Well, good morning, everyone. Welcome to day 2 of Storage Developer Conference. My name is Michael Aros. I'm the Executive Director for SNIA. Hope you've been enjoying the great sessions yesterday. Looking forward to more great interaction with our presenters, of course, the hallway track, and the Birds of a Feather sessions this evening, as well as the Plug Fests that are going on today. Briefly, everyone here should be familiar with SNIA, but quick recap. We're a standards organization. In order to do standards and deliver on those, the value of those standards to the industry, we also do interoperability and conformance testing. In addition to that, when new technologies come out, there is the need to do additional focused education, promotion, acceleration of those technologies and their adoption in the industry. Towards that effort, we have technology initiative groups that do just that. You, the companies in the industry, come together and contribute and work together as competitors for the benefit of the industry to deliver and accelerate those new technologies. My mic is on or not? Sorry about that. And also part of our, now I can really hear myself. Part of the SNIA's charter is education, vendor-neutral education on a variety of technology and standards for everyone in the industry. Most of us here are seasoned professionals in the storage industry, but we need to constantly remind ourselves that we have new people, new college graduates, new entrants into this field that need to be educated on the fundamentals of storage, some of its history, how we got here. That history and education on those fundamentals are absolutely critical so that we as an industry as a whole will not repeat some of the mistakes of the past on interoperability and other such challenges that we've had and we've dealt with already as an industry. We do have a certification program as well, vendor neutral, and of course, SNIA events. You are at one of those events today. Thank you for joining us here in September. Other upcoming SNIA events, we have our annual members meeting conference. This is where we report on SNIA's activities, financial status, as well as plans for the year ahead. Those are welcome. All SNIA members are welcome and encouraged to attend that call to hear from the chairman of the board, our treasurer, and myself on those updates. It's a 45-minute call. We keep it brief. Please do join if you are able to. We also post related materials for you to review offline if you're unable to join. Our next face-to-face meeting will be in January, back here at our home away from home, the Hyatt Santa Clara. Encourage you to join us there. We have the pleasure of having Andy Bechtolsheim be the keynote for that event, a visionary and seasoned veteran of our technology industry to share his insights and views. Co-located with that event is also now another event that the industry has become accustomed to, an annual update on what's the latest that's happening in persistent memory world. We'll have the Persistent Memory Summit that week as well. Please go register for that event. It is free to attend the Persistent Memory Summit. Thanks to our sponsors for that event, as well as the Solid State Storage Initiative Group within SNIA, one of the initiatives that sponsors and promotes education in that technology. This is a quick snapshot of, these are the active standards in development within SNIA currently. We cover a tremendous range of areas within storage, from additional refinements to persistent memory, to cloud. Computational storage is one of the groups that was formed a little over a year ago that has seen tremendous interest and participation from the industry. Long but not forgotten, tape. We're still doing updates to the LTFS spec there. Still continuing to deliver value to the industry, and therefore still having industry players continue to refine and evolve that spec. On management, on power, the SNIA Emerald program, and of course on security, object drive, and several other areas. If you want to learn more about those, please visit the SNIA website. We have more details on those and how to get engaged as well on that technical work. Another group that we've added now a little over 3 years ago within SNIA is the SFF group. It's a technology affiliate. You may join this group without joining SNIA Core. It's one of the benefits or arrangements we've made for the industry. We realized that the form factor in transceivers was a little bit, it had some specific needs, so we've enabled that capability. And by the way, that technology affiliate is available as well for others in the industry who have ideas or groups they'd like to start or work. SNIA would be happy to work with you and consider being a home for such future work within that construct and structure. This is an example of the technical work that is underway there currently. This changes extremely rapidly. This group, generally within 2 to 4 months, they started and finished and published the spec. They move at incredible speed with great efficiency. If you have a connector or a transceiver or other form factor related things that you're considering in the industry, this is the home for it. There's over 68 companies within the industry that are members of this group. Please bring your work here. Please help us consolidate and not have separate work happening all over the map within the industry. This is the place. We have a very familiar IP policy that the industry's bought into and a very efficient way on how to deliver on your needs. International. SDC is not just in the US here in September, as you've come to know it. In the last 2 years, we've added an event in EMEA, being hosted in Tel Aviv, Israel. This will be its 3rd edition in February of next year, as well as SNIA in India and Bangalore, where we do an SDC. Please help us support the international developers. If you're able to sponsor, participate, either to present or join those communities, please do. Really appreciate it. In terms of the event that we are here, really wanted to thank all of you, the sponsors, the attendees, the speakers, the agenda committee, the staff who have helped put this event together. Hope you've been enjoying the sessions, the quality of the sessions. I will ask you, please provide us your feedback. I will ask you that again at the end as a reminder to let us know how we're doing, what we can improve. But a huge thank you again for the sponsors on the screen. They make this event possible and keeping the costs reasonable for the attendees. Today's schedule, everyone should have their agenda in hand. I will highlight a few things in the program. Please do grab one of the guides that team has put together if you don't have one handy, or download the app, please. If you do search by SDC 2019 full within the App Store, or just use one of the QRE codes. As mentioned at the beginning, there are several plug fests going on within the construct of this week at SDC. One of them, the long-standing SMB3 Plug Fest that is sponsored by Microsoft in conjunction and partnership with NetApp. You can see the logos of the companies that are currently participating and doing work on that interoperability testing downstairs. They held an open house yesterday. If you didn't get a chance to attend, feel free to ask any of the staff to give you an introduction and to let you know how you can participate in the future in that event. SNIA Swordfish is one of the management standards that has been rolled out in the last couple of years in close collaboration with DMTF, rolling that into the Redfish spec. A huge thank you to the Storage Management Initiative, who's been promoting and supporting that. There is a workshop today that starts 2:50, gives you a little preview, a little teaser, and then during the reception in the evening, please visit them for hands-on opportunity to test out this new storage management technology. You may have seen the hackathon signs around as well. A big thank you to the Solid State Storage Initiative. This is part of their effort in the industry to educate the developers, hands-on opportunity, and experts available on hand. Stop in there to learn how to program for persistent memory and how to get your software to take advantage of the technology. There are sessions during lunchtime that you can pop in there, but really the experts are there all day long. Whenever you get a chance to jump in there, please do. We have a full agenda today for general sessions. We have four great speakers and topics lined up for you. It will be my pleasure to introduce the first speaker here shortly. Please also remember the Birds of a Feather sessions. We started last night with 2 great sessions, extremely well attended. Now, this evening, we're doubling down. We have in parallel sessions during those time frames, so you'll actually have to make a choice which one you commit yourself to. And as promised, reminding you again, please submit your evaluations. We need your feedback, really to, if nothing else, tell us we're doing great. That at least gives us, but we do seriously spend time after the conference reading through all your comments, your ratings, and look on how to improve this conference for your benefit in the future. Last, I wanted to leave you with a quick thought for the day and for this conference. When you see this image, this color, it brings to mind, what does it bring to mind to you? Brick wall, maybe some yellow, some warning sign of sorts, right? Well, when we continue to evolve and take another look and some other fun patterns of hexagons overlaid in a neat fashion, what happens when we continue to expand our perspective on it? It's an indicator, right? But I wanted to use this kind of sequence of events to just convey to you that perspective is important. If you're too close to a problem, you may not be seeing the whole thing. You may be seeing a problem, when rather, it's an indicator that's trying to keep you away from the weeds and the drop off on the left-hand side and keep you on the road ahead on developing new technologies and not falling into the not so fun drop off on the left and off the mountain. This is what by coming together from the industry, we can help each other. We each come from different education and perspectives and company objectives. But by bringing those perspectives and sharing them with each other, we open each other's eyes to new possibilities on how we can work together and move forward as an industry in advancing the storage technologies for our mutual benefit. Thank you. Have a great conference and enjoy all that we've put together to you, including the hallway tracks. So while we're switching laptops here for our first presenter, it is my pleasure to introduce Roberto Pion, software engineer from Facebook. We're excited to welcome Facebook, who's been working on improving video-related infrastructure across networking, computation, and storage. Before Facebook, Roberto worked at Google for 12 years, with the last 2 at YouTube. Prior to Google, Roberto implemented real-time augmented reality for sports TV, including for those football fans, that yellow line that moves the goal line, the line of scrimmage, and on NASCAR, for those fans, the pointers that are on the screen there. So with that, thank you for joining us.
Thank you.
Look forward to a great presentation.
All right. Hello, everyone. Let's make sure. Thank you.
And please give a big hand welcoming Roberto.
All right. So hey, I'm Roberto Peon. Good morning, everybody. It's early in the morning for some of us, certainly me. Thank you for being here, and thank you for letting me talk about this. I think it's going to be fun. So let's talk about abstractions. After all, as we know from multiple famous quotes, all problems in computer science can be solved by another layer of indirection, aka abstraction. So let's jump into this by figuring out, like, why am I here? Like, why am I talking to you? I'm supposed to be working on video, right? Well, it turns out that for a large-scale video site, there is a wealth of different devices, and they're uploading a wealth of different formats, and they're at different bit rates, and they have different codecs, and they each have different lengths. And so basically, it turns out that there are many different kinds of video and video playback. And even worse, not only are there different inputs, but there are many outputs. And they can each be consumed quite differently. And so in particular, here is an example of what large video processing site may kind of look like. And you notice that storage is kind of in the center there, and it's probably for a reason. And all I can really say is that processing video at scale really requires a bunch of system components working together. So let's talk about video. It turns out that chatting with my mom on video conference is really different than playing that new Netflix series, or watching that new Facebook Watch thing, or whatever is your favorite video channel. And by the way, chatting with my dad has different requirements than chatting with my mom on VC. Right? And the audio part of that has different requirements than the video part. And not all parts of the video, video being a stateful thing, are the same either. And so much so that even as we transfer this stuff along this internet that has become so useful for us, there are different protocols for this. And just off the top of my head, there's RTMP, WebRTC, variants of Dash, there's HLS, and you can probably make up a whole lot more as you go on. And this brings me to kind of the problem. Like, why did I get here? Like, well, I'm lazy. I hope you are all lazy too in this way, because hopefully it's in a good way. I'm lazy, and that makes me not want to have to solve the same problem again and again and again. I want to solve a problem once, if possible, and then map it to all of the other times I have to do the same thing. So the way this translates for me is I want to reuse code. And I want to reuse it for video conferencing and live broadcasts, 1 to millions. And for VOD video, I've uploaded a cat video. And I want to do it between real time and batch, right? And I'll point out, like, from a statistical sense, if I'm not reusing code, I'm increasing the amount of time necessary to achieve a particular certainty about a result, right? Statistic is statistics regardless of the field you're in. And in other words, there's a lot of value in reuse, right? If I want to move my system, my video system, faster, right, I need to be able to trust the components upon which it's built. I can't just reinvent everything every time. That's going to be really slow. Just in an experimental sense, I'd have to take a long time and a lot of experiments to get certainty about what I'm doing. So sadly, when I got to Facebook, there was no abstraction that would allow the reuse of code across all of these different video use cases. As a reminder, if you're doing video conferencing, surprisingly, you prefer LIFO over FIFO. You prefer the new data over the old data. You prefer low jitter. You don't want to talk like that, right? We humans have our own built-in protocols for flow control and retransmit, right? We don't need some other layer to attempt to do it for us. It confuses the heck out of us, apparently. You know, and so when ingesting a new movie, however, you really want all those bytes, and it's okay to retransmit those things. That's fine, all right? So, like, how do you solve this? As intimated before, add a layer of abstraction, as usual, right? So let me ask you a question to think about in your mind. What I/O abstraction works for partial reliability, right? Partial reliability, to remind everybody, means I may want it retransmitted, I may not want it retransmitted. I may want it retransmitted within a certain reliability window, right? So what abstraction works for that? And if I had to guess, what many people would think is maybe datagrams or something like datagrams, right? And I already see some head shakes, and I think I agree with that. Datagrams are insufficient, right? You need an ID somewhere in that datagram in order to reorder. And once you put an ID into that datagram, guess what? It's not a datagram. It's not a unique atomic unit of anything anymore, right? It is now part of some different address space, okay? And you know, by the way, when you send a packet, what is the probability that it arrives on the other side? It's not 100%, right? Because it's not 100%, that means you have to deal with reordering, putting things back in the right order. And I want to remind people, I'm here because of video. And video is inherently stateful. We have these I frames, P frames, B frames. The I means independent, by the way. And all in order to deliver you these wonderful, entertaining experiences that you've probably come to enjoy. I can't do that if I'm sending you raw pixels. It's not going to work. And if I have to get all the bytes out of order, I cannot present to you those pixels in any fashion that you would enjoy. So what is my answer to this? Well, my answer to this is that you want a named stream with an offset. And why is it named? It's named because if it's not named, then it can't work. If we go back to how we make computers work at all, I think it's really interesting to realize that the Turing machine requires addressing. It requires offsets. It requires tape in the model, right? And in order to seek in that tape, there has to be some place to seek to, right? So the only way we get computing is because we have addressing. And for me, that was kind of a surprising thing to realize. And I'm going to point out that if we're thinking about other abstractions for I/O, like a socket or a TCP connection that you might be used to, that itself has a name as well, right? Source port, dest IP, source IP, dest port. And of course, in other words, we call it the 4-tuple or the 5-tuple. So it has a name. And so my observation is that this sounds really similar. It sounds like something that we've all been dealing with for a very long time, which we might call the file interface, right? Files have names, they have offsets, they have data, hopefully. And the interesting thing, though, is that I think that the file interface needs a tweak in order to handle this stuff. So if I wanted to represent a TCP stream as a file, what would that look like? And by the way, my opinion is that TCP is really a windowed log. It's not a byte stream. It's a windowed log because we need a buffer in order to do the reordering for the retransmits. That's the log part, right? It's windowed because we want to be able to have an infinite byte stream, but we have a limited address space, right? So the tweak that I want is that when you do a read at an offset that is not yet unknown, right? We haven't yet received the data for it. That read should block until at least 1 byte within that range exists, or until it can be guaranteed that that data is never going to exist. For instance, because somebody has closed the file and said they're never going to change it again. So the sockets API, right, gives us 2 different modes of operation today. Either completely unordered datagrams or completely ordered delivery of data. And in my opinion, neither of those is really desirable. Most data, as we've talked about multiple times now, encompasses multiple packets, right? I mean, it's pretty rare. Even your telnet session from ages past is going to have characters in different packets, yes, but they have some relationship to each other. So presenting your I/O in scatter-gather, which is to say every byte that you give back has an offset, has a range, but every byte that you get may not be in order. It is ordered, but not necessarily in order, right? And once you do that, then you can have proxies and stuff. And the great thing about having proxies in this case is the proxies can help you deal with terminating of that loss, that inevitable loss that happens on every network that has noise, by the way, which is every network in every circuit, all right? So I'm going to make an assertion now. That file interface that I was talking about allows for both normal in-order delivery, which is to say ye old sockets API, without any real additional complexity, but it also allows for out-of-order delivery. And once that's true, I think I probably have an abstraction that I can work with for video. Because again, I have to deal with live video conferencing where I don't want that to happen, right? One moment. And I have to deal with VOD video where I really do care about everything getting everything reliable, and I don't care about the retransmissions. All right. So why does that out-of-order delivery matter? Well, turns out most cases for video, I don't have multicast, at least not at internet scale. I might get it to work for a network or two, but on the whole, it's not working. But thankfully, we do have the CDN. And that basically implies that our solution to scaling is going to be caching. So in order to cache, I have to have the data. I have to address the data. And in order to receive that data, I have to use some API. And if I'm using the socket API, I only have the choice to use in-order delivery, which means I am guaranteed jitter. I'm guaranteed reordering problems, right? So put it another way. Imagine that I have to read k bytes at offset n from a file, and then I have to discard all the n-1 bytes. That is the socket API, right? Wouldn't it be cheaper just to start reading at byte n, right? Isn't that what we're used to with the file interface? All right, so let's zoom into a proxy and talk packets, just to pound this nail even harder, because apparently I only have one hammer. So here we go. Here we are sending packets. Isn't that lovely? Isn't that boring? And by the way, the proxy here that I'm talking about is a CDN proxy, which means we're talking layer 7 HTTP right now, but it really applies to anything where we are trying to interpret stuff. OK. So boring. All right, let's add some packet loss. Let's make this real. All right, so we got our request. And oops, we missed a packet. And in this case, we missed the first packet of the response. And there's a interesting possibility that any packet that's lost is not the last packet, and it's pretty high. And I'll point out that on the real interwebs, this can happen even on a supposedly uncontended link because of the way TCP congestion tries to probe bandwidth. So you can contend with yourself. Isn't that one lovely, right? OK, so what's happened then is that we had to wait for that packet, the one that was lost, to be retransmitted before we could use any of the bandwidth on the further upstream, right? And that's not going to be very work conserving. In other words, that proxy couldn't forward any of that response until it could fill in that hole, right? And we know this by other terms. We know this is head-of-line blocking. And head-of-line blocking is the cause of jitter and variance and all of those things that I'm trying to avoid. And oh, by the way, this head-of-line blocking is also responsible for missing out on some good put that we could otherwise use. In other words, the transmission delay is going to occur for every single one of those packets that followed that first packet, right? That's a cumulative delay because of one packet loss. So problem. Videos almost all represented as files, but Facebook didn't have a file interface. I'm going to point out that in many cases when somebody says problem, they're also talking opportunity. Another problem, Facebook had many file interfaces. Huzzah. The great thing about standards is you can always add another one. So that's what we did. We said, hey, let's add another file interface. And that ended up being this thing called OIL and Vcache that I'm speaking to you about today. And hopefully, like every other standard we add, this one is different. We're going to get into those differences. But I think one of the interesting things is that we are hoping this is expressive enough to wrap or encapsulate the public interfaces for most file systems and object stores. Right? So what I'm going to try and talk to you about is the fact that I believe that we should be thinking about how to abstract these things in a way that is consistent. In other words, I think that we need to think about innovating the abstraction, and we haven't for a very long time. So back to your regularly scheduled programming, file APIs. Who here likes file APIs? Awesome. Yes, let's talk about file APIs. You're probably used to something like this, right? Open, read, close, write, delete, blah, blah, blah. And my question to you is, what else do you need? Don't have to answer, just think about it. And let's answer that question with a question. What is stored into retval and what is in error no, given this little code snippet? All right, so I'm doing a write of some data. I've already asserted that the file descriptor is valid. Like, what is that return value? All right? And my response is that the question's ill-formed. It depends on the file system. It depends on the quota, the capacity, the load, the contention on the network, the power situation, the heat situation. I mean, it's a trick question. So let's go to another little situation to try and explain this. So what if write is speaking to a distributed system, because nobody here has any of those. And you want to have 3 replicas for safety reasons. And 2 hosts fail the write and 1 succeeds. Here we go. Right here, we are starting off. We have our client who's doing the write, and it's going to try and talk to these 3 things. And oops, 2 of them fail. OK, so what's the return value for this system? Right? For banking, that's going to be a hard no. Thank you very much. I like my balance to actually make sense, and so does the bank. So the bank, they really care about quorum. They really want consistency in their system. And if they can't have consistency, they're going to give up on availability. Thank you, CAP theorem. But for video conferencing, hey, 1 out of 3 ain't bad, guys. You know? In the video conferencing case, we're good to go, right? So here we have 2 examples where we have the same write call, we have the same nodes, and yet the response is different. Wait, what the? How do we encode that in somewhere, right? So the answer to something apparently as simple as, does write return an error, depends on the trade-offs of the file system, which tends to be correlated with the trade-offs of the application that people are trying to solve. And we know, by the way, that the P in CAP, the partitioning part of CAP, that's really not optional. Any real system is going to have to deal with partitioning. That's going to happen. Right? So you only get the choice between C and A, or CA and price in most cases. So there's no single correct answer to that question, as we already saw. So why should you care? And I would say, in the case of a single host, those failure domains overlap, and you probably don't have to care. You can pretend you don't need to care. It's good enough. But to typical distributed systems, at least today, those failure domains are so separated and distinct, you probably do need to care if you're going to have a system that people actually want to use. So although, in theory, your computer is internally a distributed systems, and the buses are networks and all that kind of stuff, in practice, they're a bit different. And that's probably why our file APIs look the way they look. So other than what I talked about before about just having read block when data is missing, although I do think that is cool. And I think that we should have an API that works for the single host case and at a large distributed system. And I believe that the cost for this abstraction should be low enough on the developers that they actually want to use it. Because otherwise, we can come up with all kinds of fairy tales and rainbow dust, and it's not going to happen. And the basic idea of this proposed new API is be explicit. Say what you want. Say what you expect. And hopefully, it doesn't have to be that hard. And I'm going to show you a snippet of code here that gives an example. And you will note it is more complicated than the prior code. But hopefully, this would be at a lower layer than what you would use. Because hopefully, the application ends up defining its own right. But the basic observation is we're going to give a policy DAG at the point where we are creating a file. And this policy DAG is going to tell us what should happen in that case where there was 2 out of 3 that failed and 1 succeeded, all right? So first point, create requires a DAG. And that DAG is a specification, which I'll get to later about what that is. The DAG defines a virtual file system, kind of on a per-file basis. So I could have what appears to be a completely different file system for any file I create. Practically, people are going to have some set number that they use at any one point in time. They're probably going to change those over time. And I'm not just talking about because my video is 10 years old and the chance that somebody's going to watch it is about the same as lightning striking me here on the stage right now. But also because people have applications that change in their latency requirements, their storage requirements, and all that kind of stuff over time. Operations should have multiple returns because there are at least 2 phases that are interesting in any I/O. And one is that the I/O has been satisfied, and the other is that the effort is exhausted. And satisfied means that the application has said, hey, I can make forward progress now, right? And exhausted means that there's no more work happening in the background, and I can probably deallocate all of my buffers or any such thing that I have. And by the way, the lack of one of these is always going to cause a problem, either in latency and jitter or in ooming. And we all love ooming because that makes forward progress so easy. So let me ask a question that I had to ask myself, like, what is a file system? And for me, the definition is that it's a mapping of name to byte stream. And really, it's 2 mappings. So there's name to something, and then offset to byte, right? And then the something is really metadata, right? Like, this file was created by blah, it's in this place, this is its name. Maybe this is the encryption key, because we love encryption at rest these days. And so if we're going to be explicit about everything, then not only do we need to handle like the data part of this, but we need to handle the metadata. So this DAG, 2 to be true in this case, says that for metadata, I'm going to write this metadata to database A. And by the way, these nodes represent systems, not necessarily a specific instantiation, not necessarily a specific host. Okay? But they could be that, depending on what the DAG author is trying to do. So, and by the way, these could all be on the same machine as well. So I'm going to talk to database A for my metadata. And for my data, I'm going to talk to 3 different file systems here, A, B, and C. So let's go back to this. What is a DAG? I hope we all know. But it's nodes and edges. And it's nodes and edges that don't go in a circle. In the context of this new thing, like what is a node? A node is either the built-in race node, which I will get back to, which says how to use its children and when, or it's a storage node, which represents a potential storage location. Each of these nodes could have a transform stack to say how to transform the address space and the data that we want to store in that apparent location. And I'm going to point out that this is a potentially strong win for efficiency. Because let's say I want to encrypt something on disk or at rest, right? Do I need to encrypt it every time I send it to the storage medium and then decrypt it every time I read it from the storage medium, even when some of those storage mediums are buffers somewhere, right? That would be kind of sad. How about I encrypt it once and then know it's supposed to be encrypted in a bunch of locations and then like just shove those bits across the wire and write them? Right? It would be a waste to have to unencrypt them and re-encrypt them every time unless you have a specific purpose in doing so. Some other example transforms, chunking. Hey, if you have a, I don't know, 25 terabyte file, do you really want to try and write that in one storage device? Well, that would be a little problematic, right? Because we don't have all that many storage devices that large. And if we were worried about things like, caching, where you probably have RAM, whether it be DRAM or NVRAM or some other variant, you probably want to be able to actually fit that into your device. So you probably want to chunk it. And we know that loss happens, so how about some read-Solomon or other FEC? And we know that entropy happens, so how about gzipped? And of course, we talked about encrypting. So chunking is by far the most common transform that anybody wants everywhere. Every single phone in everybody's pockets does this in the form of virtual memory. It breaks stuff up into pages. These pages are written ostensibly a little separately, although the file system glues them together, right? And the idea here is that since every node in that DAG that I presented before is explicitly labeled with the transforms that we want to do to the address space and the data, anytime you want to write from one to the other, you just simply compare those stacks of transforms, and if the stacks are the same, you don't have to do anything more. All right? So here's some examples. In the top example, I'm chunking at 1 megabyte, and I'm encrypting. And I'm sending to another node that's doing the same. Don't have to do anything. In the next node, the chunk size is different between these two things, so I have to re-chunk, which is incredibly cheap. And in the last one, everything is different, so I have to unencrypt it, and I have to re-chunk it. All right? OK, so that race thing, this is the clue. This is what makes the magic happen. And it's my favorite part of this new oil thing. So race is a built-in node. It's not a storage node. It's what we would call a virtual node or some other thing like that. And it expresses that when a certain number has been exceeded, the operation is satisfied and can make forward progress. So you see num until satisfied is 2 in this case, which means 2 children would have to return that they are satisfied. And then this node would return it is satisfied. OK? And then the next line here says num until exhausted. And as a reminder, exhausted means I'm not going to do anything anymore. It means I'm done. But we wanted to avoid saying done because done typically implies success, and exhausted doesn't necessarily imply success. So num until exhausted, in this case 3. Staggered start delay, because we all know that when we have 3 replicas that all supposed to have the same data, we should always read from all 3 of them in order to supply the user's response, right? That would be wonderfully work-conserving and cheap, right? So a staggered start allows us to talk about time, not just about what the semantics of completion are. And lastly, concurrency. We might not want to try every branch at every time, regardless of time, right? So we want to talk about max concurrency. And it turns out that this little node here is expressive enough to allow you to define an if-then-else chain. Any if-then-else chain, really. If that, OK, great. So basically, in this case, what happened is we did file system A, and that didn't work. So then we did file system B, and that didn't work, so we did file system C. Right? And as max concurrency of 1 implies a serial behavior, right? This implies that in this particular DAG, the nodes have to be visited from left to right. It's also expressive enough to describe try all, because there are actually cases, like when you're doing quorum reads for something, where you do want to try all of them simultaneously. And in this case, we changed max concurrency to 3. And as you'd expect, that's fully parallel. And it's expressive enough to describe a quorum write, right? So in this case, what we did is we now have number of satisfied 2 out of 3, right? And as long as 2 of those come back, you're OK. So remember that question I asked before? We had 3 different places we were going to write to, and we said, hey, what is the return value for this? Right? Well, I'll point out that num satisfied 2 answers that question. That the return value, if 2 of them succeed, is good. Forward progress can be made. That means that we have told the write call what its response should be in this policy. Not just how to do the write, but how to interpret the success or failure of that write. All right? So let's go back and talk about storage nodes in this DAG. Like, what could those be? They could be things like a local file system, Haystack, HDFS, a block device, somebody else's block device, a remote block device. Anyway, they could be anything where you want to store something. And by the way, they could also be something where you don't want to store something, which is useful for testing. So maybe I want a null device somewhere or a tracing device somewhere, right? Because these are policies, I can insert such things and help me debug my system. I can put fault injectors into my system to say, hey, well, what happens if my metadata server over here goes away and such like that, right? And I can do so without disrupting things, or hopefully without disrupting things. So what does it take to add a storage node into this thing? Of course, you have to write a wrapper. And you often have to write 2 wrappers, one for the metadata and one for the data. And it's mostly boilerplate, as I think one would sadly hope. So data nodes must express things like pwrite, pread, probably stat, a few other things. And metadata nodes must express a put and a get, because the metadata is not streaming. It is atomic, unlike the data, which can be streaming. So what about the edges in the DAG? Like, I talked about the nodes, and I said you can wire these things up, but like, what about the edges? So the idea is that the edges could also maybe express the protocol or the QoS that you want to use, because again, not every portion of somebody's read is equivalent. One other thing that's really interesting here is that when this DAG is executed, we are building up a stack as we are progressing down into this tree. And so we're passing a dictionary of read-only values into each node as we proceed downward. And let's talk about another thing that is super important for anything I/O, because all of our I/O is effectively this. What about buffering? So you notice I've talked about oil, but I haven't talked about this vcache thing, right? So it turns out that it's not an afterthought, that one of the reasons why we had to build this in the first place is because we had to think about buffering. That buffering was intensely critical, not only to deliver on the user's latency expectations in many cases, but also because you actually want to process the data in ways that don't strand your compute units just sitting there waiting for stuff for a long time, right? So in addition to that DAG, we also have a vcache storage node. So in putting those together, we get oil and vcache. Oil is the output-input language. Aren't you happy I defined that now? And vcache is the virtual cache, or the virtual memory cache. The V, surprisingly, does not stand for video. Because I'll note that on every big machine that we actually do computing on, we have virtual memory to try and abstract away the storage from the application. But apparently, in distributed systems, we forgot about that. So here we are relearning, or at least I was relearning. So vcache knows about dirty pages, clean pages, and files. It's accessed using oil DAGs, and it knows how to talk oil out the back end for evictions. So it's different from other caches because it understands oil on both sides. It also does stuff like understanding dirty pages. In other words, it is a write-back cache, which is different from some. And because it's written to and evics using oil DAGs, the DAG that we hand over represents a holistic policy. This policy doesn't terminate at any one node in this DAG. Everybody in this DAG can understand where they are participating in that DAG, right? And why would you care? And I'll say again, in my opinion, real-world performance is going to be dependent on how you cache and how you buffer, right? That is where we get most of our performance, given the non-uniform access times to many different places in storage. So vcache understands various write modes, as you would expect. Write back immediate, so your operation is asynchronous. And write back lazy, and all those other kinds of things. And the programmers do use them sometimes. Most of the time, write back lazy is what most people want, because there's a reliability trade-off you get by giving up what I'll call knowability. What about the read path? Well, it turns out reads often have side effects too, although we often forget them. In the cache, a read can cause a cache insert, or it can cause the item to be promoted to the top of the LRU, right? And these have significant impacts, and I'm not going to go into it too much because we have limited time. So what about virtual memory? The interesting thing I came to realize is that the kernels in the various operating systems are all providing a super interesting abstraction. This key byte stream thing that I'm using actually is represented in multiple places simultaneously within the system, right? It's in the L1, the L2, the L3, it's in DRAM, it's in the drive's buffer cache, and it's probably on the drive's storage itself. A piece of data exists in all of these locations, not one of these locations. And in the typical I/O system, we imagine that the data is stored in one place, not that it can be resident in any of these places, right? At least that was new for me. And so that is true of vcache. You can have a vcache that's localhost only, right? So it has the same failure domain of the host in case we want to have those kinds of system properties. But you can also have ones that are remote. You can have ones that are remote within the same rack, data center, et cetera, right? So a vcache then is going to be accessed by saying, I'm going to talk to this vcache, And I want to talk about this file name or this object. So a real-world example here. I'm going to have a local vcache, which is going to race to a quorum of remote vcaches, and then they are going to write out to some other file system asynchronously. Right? This is going to allow me to absorb a high number of IOPS, provide a reasonable performance, and still store stuff permanently. Right? Okay. And let's see. So it's a cache hierarchy, right? We have multiple caches. We go through one to get to the other. We can do different hierarchies on read versus write, right? All right. So why bother? I'll point out that you don't often know when you're running a large system if the processes that are communicating are on the same box or not, right? And if they are on the same box, it's way faster to just share the DRAM than it is to serialize over the network, put it through a socket, put it through the stack, unserialize it, read it, right? That's way more work for our boxes. So we can do better by understanding where the reads and the writes are homed in a specific circumstance. Another thing about metadata, so consistency is pretty darn desirable. And so these DAGs are expressive enough to express Paxos, it turns out. So you can actually just have a policy as opposed to a system design that allows you to assert whatever consistency you want. And you can do this on the metadata as well as the data, because remember, CAP theorem says you get to choose C or A. P is not optional, except for price. Okay. So the metadata, as a reminder, is the file name, the leaseholder address, all that kind of stuff. And the address of any particular piece of data is computed using the offset plus the file name and the data DAG. So here's an example of Paxos. This is a DAG that could actually work. I'm not going to go through it too much, but you see that describing Paxos in this little policy language is actually pretty simple. And as an aside, in my opinion, everything is a cache. That file system that you are working so hard, that storage you are working so hard to build, it's a cache. And it might be controversial, but what is a file system? It's a cache with the policy of reject new, right? So when I'm full, I'm going to reject the new stuff, right? And here's how I can prove it. I have 3 hosts. They all have 1 terabyte of space, and the user wants to write a terabyte of logical space, and I'm replicating the write to every host. How much space is there? How much data is lost, right? None. But now the client is going to buffer. Wait, what? What happens when the clients go away? Right? OK. So as before, there's a trick question here. Like, which of those scenarios happens depends on the eviction policy that you want to use. So what would happen if the nth replica was evicted for the n-1th replica in this proposed system? Right? So I'm reducing replication. Why do I have replication in the first place? I have replication because I want reliability, right? But in the case where I was requiring that replication, I had a 100% chance of losing 2/3 of my offered data, right? I had a loss of 66% of my data, right? However, if I had simply reduced the replication amount and each host had a 99% probability of being up, right, I could store all of that data and lose at most 1% of it. So thinking about everything as a cache implies thinking about how these systems fail in overload, right? That's all a cache is talking about. It's talking about a policy to associate with a resource, right? And making an assumption about what is appropriate for a user is likely to be wrong in many cases. So in this case, we try not to, right? We try to have the user be explicit about that. So as a reminder, problem. An abstraction with multiple return values doesn't look like POSIX, so how would you use it? And the answer is, hey, new applications can use it, I guess. And maybe the old ones use a fuse mount, where they can at least express that policy or the policy name. So what they are using looks exactly like a file, but they can actually still define those different dependencies, and they can define those different trade-offs that they want to have. So they can use the regular POSIX interface, have an answer to that, what should my return value be, not get quite all of the wonderfulness, but 90% of the wonderfulness. And if you have a hierarchy involving multiple layers of a system, how many I/O attempts will occur? So yeah, I have k layers, and each retries n times, right? K to the n. I don't think that's what they mean by try to grow your business exponentially, right? Effort should decrease as the system health overall decreases, right? So each I/O can use a sub-DAG. Each I/O can be told, hey, this is how much effort I am doing, because this DAG expresses holistically how you're putting these things together. You can talk about how much effort holistically you want to use. So I can have 3 layers. Each could be allowed 3 retries, but as a sum total, I'm only allowing 3 tries. Right? So I can prevent exponential retries while still allowing retries to occur at each layer of the system. We allow per I/O customization. So if I'm doing a file system scrub, for instance, I do want to access every single location. I want to read every byte that I can read to see what is missing so I can fix it, right? So just because the user has defined a policy once doesn't mean that they want to access it in that way forever, right? And it doesn't mean they want to change it either for the application. It may mean that the system wants to use it differently than the application does. For instance, you want to target specific parts of a DAG. I want to read from that node to see if it still has the data in order to fix it. So there's more, but I don't have time to cover all of this in depth. We could probably spend forever talking about this, and that would be a bad policy. So migration, moving data from one DAG to another, because again, policies change over time. We have a coroutine-based implementation. I can say lots of good things. We have some real-world data. What I can say is it looks good at this point. We have looked into maybe peer-to-peer caching of hot data. So if you have thousands of hosts all attempting to read the same thing, we can scale the number of places that actually can serve it. And we can do this without doing peer-to-peer all the time. You do read, scatter, gather, write. By the way, mmap and remote swap with this kind of policy stuff could be very powerful. And event filtering, because not every application and every level of this DAG wants to receive events from everything beneath it over the ocean, right? So bringing it home, I think oil and Vcache is cool and interesting, but that isn't the real point. I'm hoping that this makes you think and rethink ye old storage abstraction. Should it be what it is right now, or should we innovate there and change it and fix some of the problems that occur when you make a choice, any one choice about many things? That's all I got in the presentation. Thank you very much, and questions? Any questions?
Source code?
Yeah. Source code. Maybe eventually. The team is definitely interested in open sourcing what we have here. But end of the year is approaching, and various other pressures make it very difficult to spend time open sourcing stuff right now. So the idea is that we will open source what we have eventually, but even if we do, I think that what we have in our implementation is less interesting than you thinking about how you would want to do this. Because the core of this, that race node, I think anyone here can implement that. Or they can hire someone to implement that if they want to. The real core here is just rethinking what the storage API should be, because it's been causing problems, at least I think. Any other questions?
What does it mean for the actual media, like SSDs or hard drives? What does this mean for the actual media, hard drives and SSDs? Does it mean that those can be more unreliable, or?
I think it means that it would be easier for a user to meld together unreliable things and still have a system that appears to be reliable. That's not the same as saying I would do that. But the observation is that these things are inherently unreliable even when you think they are reliable, because the media itself can be reliable, but the system upon which it's built cannot be. So if you want true reliability, not only do you have diversity in terms of locations and replication, but you have diversity in terms of systems, right? And that's why, as my understanding is, the space shuttle and various other things where lives are on the line, they have system diversity in how the things are coded and presented, not just the locations.
One last question.
Last question?
Thanks for the presentation, very stimulating. I have a question specifically about how you represent nodes in the DAG. It seems to be very specific to how things are replicated, etc. Would you rather that the user specify how durable or consistent or available the data should be?
So one of the APIs that we have been working on is kind of the DAG chooser or the DAG creator. And of course, there's an infinite number of variations, or effectively so large as to be considered infinite. And so what we are imagining right now is that we create some number of things that we think we like, and we map them onto various use cases we think are interesting. We are also been talking about having introspection on the node, so the node can say, hey, I'm a write only, or I'm a append only, or a write once kind of thing, so that you can basically prove properties on the DAG, like everything's encrypted at rest for a bunch of stuff that matters. In other words, the idea is that the user could present a bunch of properties that they want, and then we can select amongst the DAGs that have been described, and if those don't work, maybe try to synthesize another one. In other words, selection of the DAG is wholly separate from the implementation and use of that DAG in the real systems. Thank you so much, everybody.
Back, and welcome back to our live stream viewers as well. We're continuing our excellent lineup of main stage speakers this morning at Storage Developer Conference with Rebecca Weekly. Rebecca is Senior Principal Engineer and Director of Cloud Platform and Solution Strategy at Intel, where she provides a deep technical understanding of cloud data systems configurations to deliver a $10 billion product portfolio. Rebecca's responsible for looking across cloud compute, storage, networking, artificial intelligence, software, and security solutions. However, in her spare time, I don't know where she has that, Rebecca's the lead singer of a funk and soul band, Sinister Dexter. We got that right? She was professionally trained in dance, and she's an experienced choreographer. So welcome to an excellent presentation from Rebecca.
Or dancing. Not at all. I wish, no. Totally different part of life, but really exciting to be here with you today. I spend most of my time with our customers, with our cloud customers in specific, whether the hyperscalers or customers who are leveraging their own internal clouds. And it is such a great opportunity to sit down with the developer ecosystem and to sit down with the teams doing industry standards, because so much of the complexity that we are dealing with, you bring calm to that chaos. And if we can partner well in the standards bodies, we can really come up with innovative solutions that support multi-cloud and edge and all of the different pain points our customers are facing. And I loved hearing from Scott earlier, just before, because he is the perfect representation of that combination of on-premise requirements, what's happening on client, what's happening in the public cloud, all of it coming together as a pain point. So great experience to listen and hopefully learn, and hopefully I can learn from you throughout this session. So I'm going to start with just an overview of sort of the pain points of data, right? And I'm sure all of you know this, but this is from Raconteur, which is an interesting visual picture of data. What we're looking at here is just the data generated in one day, right now on the internet. That represents over 500 million tweets, 4 petabytes full of exciting information being generated by our customers on Facebook, 294 billion emails sent through public entities, 4 terabytes of data from each connected car, right? Each of these new IoT applications is generating a huge amount of information to be processed. 65 billion messages on WhatsApp, 5 billion searches a day, and by 2025, the estimate is that it will be 463 exabytes of data each day globally. I don't know if you're all ready to build as many wafers as we will need to supply this, but it's the innovation these teams are driving that will make sure our world doesn't melt trying to actually supply, compute, process, move, store this information, right? We've got to be really innovative as a community to address this kind of pain. Another key area and pain point we're hearing from our customers is this concept of data gravity, right? As more interesting applications are occurring in the market, whether that's AI, HPC, areas of media like what our friends in DreamWorks were talking about, this idea of bringing the data to where you are processing it to give users better experiences is incredibly important. But as people who are constantly solving the cost problem of storage to address that 463 exabytes of data being generated in a day, we have to come up with cost-efficient solutions that allow you to store where you don't care as much about performance and move data, keep data where applications need to process on it. And this is a massive pain point and challenge that we are all innovating around right now. When we really think about that concept of data gravity, this was a concept that was coined by Macquarie back in 2010, and it was really that trade-off of latency and throughput, right? Stronger reliance will create a pull-through for one or the other. That's the challenge that we're trying to address in this particular space. So, oh, somebody's getting a phone call. The second characteristic we really see here is that the more data is accumulated on those edge and endpoints, the more pain in moving that information across, right? This is the network bandwidth. When we sit down and talk about TCO models with our key customers, the backhaul bandwidth is actually the major pain point, and it's regionally very different, right? We talk about pain a lot in power and power utilization. We talk about it in the cost of the media, particularly memory. But the backhaul bandwidth and connectivity to edge endpoints is a huge problem. So as they are doing more digital services work, as they are doing more AI at the edge, that is really where we've got to figure out the right efficient ways and the right APIs to actually process on that edge rather than backhaul everything to a core data center. So really thinking about that spectrum, right? That rapid growth of data, the concept of data gravity and that pain of it, and then the need to architect and build storage solutions that go from the edge all the way to core data center is the challenge that this community has to address. To do that, to accelerate that, we obviously are working on different solutions. And I'll talk about some of them today within Intel. But I think what we need to work together as a community on is those industry standards. I see no standard for how to do storage processing on the edge. We'll talk about some solutions that we are working on in the software community, but that's an area where this team needs to innovate to solve the problem that Scott was talking about, where we actually want to use GPUs in a public cloud, but we want to have an efficient way of bringing that data to the cloud where they need to process it. Okay. So just to kind of level set on the basic storage trends, right? Everybody in this room probably knows this far better than me, but what I work with and talk to customers about on a daily basis is where NVMe storage is really taking off. This is not to say that hard drives are going away. Everybody likes cheap storage, and hard drives will continue to exist. But we definitely see NVMe storage as a standard building block within our customer base at this stage. NVMe over fabrics is also an area where we're seeing mainstream deployments at this stage. It is increasingly replacing SAS, SATA-based solutions. Now, there's also this kind of new high-end performance in storage that's occurring. And this is where concepts like computational storage, where you're actually doing more of the computation on top of the device itself or on the server that is host for that primary device, is occurring. And this is where we are keeping our eye on it. We are definitely working with our community to drive different solutions, but there's no one recipe. We see different SDN-associated computational storage solutions with one top account versus others. And so that diversity in approach means we don't yet have a single solution. There's not one good architecture to solve this problem, and it's an opportunity for this community, I think, to really influence the market. So again, data storage paradigms, you know this quite well, right? The world has evolved quite a bit. Obviously, block storage is still a primary aspect of how enterprise applications and enterprise databases are running. And file storage is an obvious transition in the market as we've moved forward. But the area where I'll spend more time today is really on this aspect of object storage and how we're really seeing massive innovation in key value structures and in how they're being distributed across data centers out to the edge, and what we can do to help and where we still need, I think, more help in this community. So fundamentally, object storage really is an area where we're seeing the most innovation in the cloud. Now, you can look at Gartner, you can look at many different customers. I'm sure you guys have spoken to many yourselves. What is actually driving their choice on storage? Gartner has their perspective on this, unstructured data workloads, the capacity requirements that are there, the fact that data is not necessarily coupled to an application or is. But these things boil down to cost, data availability, security, and actually, the way of accessing the structure of that data that is being accessed. So as we look at all of these factors, that's really what that set of 4 factors is really what we're trying to disambiguate when we help a customer find a storage solution. Object storage really started in this. If we were having this conversation 5 years ago, we'd really just be talking about these applications, right? We'd be talking about core functions, REST or HTML APIs, what we were doing to help with a specific use case, whether that was a template for VMs or some specific backup or archive, or I/O workloads, right? Is it static content? Is there a low change rate? These are the kinds of ways in which 5 years ago everybody was having the conversation. But cloud has completely changed how customers are approaching this. We can say that a data lake is an example of how that's changing, right? A large repository of unstructured information that's coming from any source, accessible to any end application using something like S3. If you're doing that, you really need to have a well-defined API layer into that disaggregated data lake. You need to have SLAs that are deterministic for the different tiers within that data lake, and a mechanism by which you're disambiguating what has been in there, whether it's log information, whether it's any kind of sensor information for an edge use case, et cetera. There's so much innovation in this community, especially in the hyperscalers, but certainly in all of our, I have a few examples up there, right? Kafka is in there, in terms of how data is being processed and stored within those data lakes, and then how we are accessing that information. It is absolutely key for our customers to build on top of these data lakes and have deterministic SLAs. And I think Scott really did a great job of queuing up that data lake is not even the one that's in your traditional hyperscaler cloud. It's actually a distributed solution from an on-prem cloud into the public cloud. So one of the areas where we are really trying to work with our customers to innovate in this space is DAOS, which is our Distributed Asynchronous Object Store. DAOS we announced it actually in June, I believe, at the PMDK Summit. It's something that we started working on for the Aurora supercomputing solution for the Argonne National Lab, which is coming to market in 2021. And what is DAOS? DAOS is really a solution that is it's an open source software defined object store, and it's designed from the ground up for massively distributed non-volatile memory. So Douse takes advantage of next generation NVMe technology. This can be storage class memory. So I said NVMe, and I really meant NVM. So storage class memory as well as NVMe. So it presents a key value storage interface and provides key features like transactional non-blocking I/O, advanced data protection with self-healing on top of commodity hardware, and end-to-end integrity. And I think one of the key areas that's interesting for distributed computation in specific is that fine-grained data control and elastic storage. This allows our users to make trade-offs optimizing performance and cost, again, fully open source. Now, this is not to replace scale-out storage. Again, nobody's going to come in here and tell you scale-out storage is disappearing anytime soon because of that cost problem for storage choice. But it is about creating high-performance storage solutions, edge solutions, ingress servers, anything in that category that might want to use persistent memory easily and have access to that from the application layer. So this is, again, fully open source. I've got the links in there. I believe it's on the website after. You can go look at this. There's a series of options for you to listen to webcasts, white papers, et cetera. But we're really excited about bringing this into the market and helping this community build more on top of persistent memory and innovate on key value. Another key trend in the cloud that I think is driving a totally different paradigm for storage is this concept of function as a service. Even a traditional microservices model with containers is really driving differences in storage. When we work with customers across the spectrum on function as a service, one of the key pain points is spin-up latency. Bless you. Spin-up latency or cold start times are really a massive challenge. The whole concept of function as a service is about ephemeral computing, right? I write an application, I put it in a GitHub repo, I have a trigger event that runs that little piece of Java code, and I don't need to think about infrastructure management, right? Access to all of my data is done through an API call, it runs, it does what it needs to do, and I only pay for the computation I need at the time that I need it. And by the way, I pay more for the computation I need at the time I need it. But conceptually, for new use cases, what you'll find is that users are not yet sure how much they're going to run these applications. And so it's a good way for them to experiment before they decide if they want to optimize and bring something into their on-prem cloud or build a more sort of bare metal implementation potentially that could be more cost efficient. So it's a huge area of innovation. We're forecasting that this will be about 30% of public cloud deployment runtime hours by 2023. So there's a ton of work happening in function as a service. And every time we talk to a customer, every time we work with them, security is a pain point. But the number one pain point is this concept of spin-up latency. How do we go faster? Because these are not stateless, ephemeral workloads. They need to know their state. They need access to storage. They're doing inferencing. They're doing rendering, right? Important workloads. This is where we've got a ton of interesting POCs happening with persistent memory. And it's not necessarily the persistence. It's really having a local cache of memory-like content that they can actually grab information from quickly at a better cost structure than DRAM. So lots of interesting work in this space. Really exciting to partner with lots of our customers. I could probably name 15 different ones doing distributed work in this area. But solving this problem for faster state recovery, essentially, for FAS is going to be an interesting area of memory innovation or caching innovation on storage throughout the next few years. So I've discussed a couple of areas where the cloud is innovating, some of the pain points, some of the challenges of going to the edge, and I hope you feel empowered to help solve some of those problems with us. I really want to talk a little bit about, as they're evolving, what can we do to drive next generation storage architectures together? So Intel is definitely doing work in the open source space from software to hardware to try and solve some of these problems. We can't do it alone. We hope for your partnership, definitely. I can hit a few on here. This is an eye chart, but I can hit a few on here, I hope, to help you understand some of the areas that we are working on together. Intel Storage Acceleration Library. How many people out there have used ISA-L? Oh, it is a depressingly small number of hands, because this is like free performance. Please look at ISA-L after this session, if nothing else. I remember being in a conference with my customers in China, and one guy stood up and talked about ISA-L and literally was yelling in Mandarin, but it was translated, at the rest of the team that they were just literally throwing away dollars by not using ISA-L. Customer statement, not mine. What I love about ISA-L is really there's optimized algorithms. It's used to accelerate functions that are very important for storage, right? Compression, integrity checking, hashing, encryption, things you would typically see in most storage applications. But actually, it's so well written. That session that I was in was actually for media. And it was being used in the media space on actually codec sort of how-tos in the compression side. And it's really because ISA-L has done a lot to determine a fast path through the CPU. So an example in the storage domain is Ceph. By default on Intel processors, will actually use ISA-L on the back end for erasure encoding. Other solutions, ooh, I hit the button too fast. I will get into that in a second. So other areas to really think through that we provide into the open source community is the Storage Performance Development Kit. So hopefully folks have used SPDK as well. SPDK Summit happens, I believe, twice a year. We have a lot of different contributors and folks within the ecosystem, and it runs on any processor. This is an open source solution. Of course, it runs best on Intel processors, but it is certainly one that we are really excited to contribute to the community and make sure that you are getting best performance on storage workloads with Intel processors. And of course, one that I think there's a hackathon going on as we speak or throughout the week on the Persistent Memory Development Kit. And again, this is to jumpstart this new ecosystem of applications on persistent memory and make it easier for you to get started. Two others I'll hit just very high level on this slide and then get into some of the details is the cache acceleration software solution. So if you've heard of CAS, that is really helping us provide caching capability to accelerate frequently accessed data, accelerate access to frequently accessed data. And of course, no conversation about storage can be had without also talking about the interconnection with compute and network. Right? It's all about accessing the data as you need to get to it, when, where, and how. So there's a lot that we've done within our gigabit Intel Ethernet adapters as well to talk about accelerating storage solutions, and I'll hit that in a couple of slides. We've been talking a little bit about persistent memory. Obviously, SSDs is a huge part of this as well, and a cost-effective methodology to get better performance and caching as well. So we have our second generation of 3D NAND that was optimized for high density that came out this year as well for both data center and enterprise configurations. And then we have the 4600 series, which is really optimized for caching. So super low latency, high bandwidth that is really intended for cloud environments. All of these drives, of course, we're talking about data integrity solutions, reliability solutions, and performance consistency that you would expect from an Intel processor and an Intel SSD. So you may be wondering why I'm talking about vector extensions in a storage conversation. What does floating point have to do with storage? And the answer is nothing whatsoever. But AVX512 actually supports high-speed bandwidth vector pipelines for integer operations as well. And those are used by storage systems all the time. All the time. So this is what is really exciting to us about efficiently moving and processing data. So the XOR operations that are in ISA-L actually use AVX512 in the latest Skylake processors and beyond, CLX as well. So what you're seeing in these performance results, I always hate to point to performance results in a slide, but there you go, is actually a massive increase in performance with ISA-L using AVX512 to accelerate software libraries. P plus Q, right, the PQ generation for RAID 6 calculations, Also, and for folks who are not as familiar with that, I'm sure everybody in this room is, but when you have 2 media failures without losing data, or one failure and somebody pulls a drive when they didn't intend to, or you didn't intend for them to, that's one of the reasons why we use RAID 6. You'll see we have very exciting performance improvement results with that as well, using AVX 512. And the last one is, I think, the most exciting. It's the Reed-Solomon erasure coding, right? That everyone probably is very familiar with Reed-Solomon erasure coding. This is really for protection and integrity, so simultaneously in a scalable manner. So again, I'm sure that this is not news to anybody, that erasure coding has nothing to do with wiping data, but from a branch of mathematics. And its hashing is used all the time in storage, from file system layout to deduplication, compression, et cetera. And in all of those, AVX 512 actually has a huge improvement. So across the board, we actually are seeing for storage, the Skylake processors, the CLX processors have a ton of performance available to you in that the integer operation side. So we've done a lot of work to enable that. It's in ISA-L. It's in all of the development kits that I mentioned before. So please do take advantage of free performance. I don't know why you wouldn't. So want to hit a little bit on this concept of Intel storage solutions and this real spectrum of performance and storage and memory solutions. We continue to expand the offerings here. And that might seem confusing at times. Sometimes it feels a little confusing, I think, to the market. But it's really because we have such a spectrum of needs, like we were talking about at the beginning, right? When you're going from the cloud to the edge, you may have very high performance required, real challenges around form factor, where we need to get very dense and low power, but with a lot of accessible information. Think use cases like CDN, right? A CDN is a big storage box that's running Nginx on top. I mean, it's just a big storage box. But it's in a very dense configuration, often in a co-location facility, often not secured, right? We need to make sure that those systems can run effectively with the same software strategies as what's running in the core data center. So it requires a range of solutions. So at the top of the storage side, I just want to hit a couple. We have this 4800 series of SSDs, and these are actually dual-ported SSDs. So 2 PCIe buses at the same time being accessed. And of course, that's exciting for storage arrays, right? If you really want to be immune to any single point of failure, you want to have 5 or 6 nines of reliability, you need a dual port process. So this is really, ultimately, we're getting about 30 seconds of downtime annually from this configuration of an SSD. Now, you may ask me, why are we talking about dual-ported SSDs at the same time that we're adding memory, DC persistent memory solutions? But memory is not serviceable inline anytime soon. So there is a reason to have an SSD that is dual-ported and serviceable in field, and a reason to have a local stash of persistent storage available to you in that memory footprint. So one of the things that I'm most excited about today, and actually I was chatting with Mr. Pappas before we started here, who's going to head over to another meeting and conference for CXL announcements later today, or maybe it's a seminar, a panel that he's going to be on later today about CXL. This is, I think, one of the most interesting new standards efforts Intel has spearheaded. I would argue since PCIe. You can keep me honest. I have been so excited, and our customers and our community has been so excited about this step into the open source community. So what is CXL? It's the Compute Express Link. It's really about enabling computing in a disaggregated fashion, in a standard disaggregated fashion across vendors. And Mr. Pappas tells me it's already public that not only is this Intel, and not only is this Microsoft and Google and various other players across the ecosystem that are key customers for us, but AMD and ARM have also recently, and IBM Power have all recently joined the CXL consortium. So this really is, we believe, the standard interface by which you will do coherent accelerator computation in the future. And when we talk about accelerators, it's not just GPUs, folks. It's computational storage. It's everything that we've been talking about throughout this. In fact, infrastructure acceleration is the most frothy, if you want to talk about it, conversation that we have with our customers. And why is that? Well, application acceleration is incredibly important. Application acceleration is very explicitly called by a user. A user is going to make a determination, I want to run on a GPU. I want to run on FPGA. And in fact, they have to, right? The application itself has to be compiled for that new architecture. Infrastructure acceleration is all about a hyperscaler managing their own footprint, their own cost. It's free money. The more you do that work, the more important, the more effective, the more efficient your data center operates at. It also enables new computing paradigms. So think about what Nitro did with their second generation, where they can do a bare metal interface using an SDN offload card, right, where the entire storage stack, the entire infrastructure management, the VMM layer, the security layer is all on that card. It's no longer on the CPU. The CPU is hosting VMs, or it's hosting a full bare metal stack. It's consistent, and user traffic is obfuscated from what is happening on essentially a control plane processor for the hyperscaler themselves. The more we enable this in the ecosystem, the more standards like CXL enable that kind of activity, the more efficient our hyperscalers can be, and the more the software stacks that our users are creating will be actually accessible out to the edge. So I think this is a great, super exciting time. You know, I generally get pretty excited about our technology and what these people in this room do, right? This is how we're going to innovate as a community to drive a whole new world of heterogeneous compute. And the most important application to solve is the one that is the crazy cost center, which is storage and network. I love GPUs, they're very exciting. I'm not trying to say anything negative about GPUs. It's just, this is really the core of running a data center. It is the #1 pain point we talk to about with our customers. And coherency is key. And that's why CXL is so exciting. So I get very excited about it. That's not surprising. If you're familiar with CXL, if you're not familiar with CXL, you can always talk to Mr. Pappas. But what we're really trying to do there is it's a protocol layer, right? It's a coherency protocol layer. It's running on top of PCI Express Gen 5. So you're getting that doubling of speed that goes from Gen 4 to Gen 5, and really allowing you to have coherent memory space between the CPU and any installed device off the link. So whether that's GPU cards, whether that's what we were just talking about, infrastructure compute accelerators, it's going to be a really interesting time. And we already have a series of proofs of concepts with different customers leveraging UPI-attached, FPGAs today, innovating and starting to play in this space, and it's just going to continue to take off, which is super exciting. So the CXL consortium, the SIG, is fully established. It has lots of giants in it: Alibaba, Cisco, Dell, EMC, Facebook, Google, HPE, Microsoft, IBM, AMD, ARM, lots of really wonderful folks involved and playing in this ecosystem. And I hope you will participate as well. There's 82 or something. 87 participants. So really, this is where standards work best. This is where we drive a whole new world of innovation as a community for heterogeneous compute. So I'm a little excited. Okay, so what is Intel doing to try and help you with performance, workload placement, and really getting more out of the hardware, the commodity hardware you buy? I can talk about, I've already hit a lot of these software stacks, but SPDK, this is where with NVMe we saw a 5x improvement on FIO. So this is measured on FIO. Great speed test, most people have done it. SPDK gave us 5x, that's about 7.8 million IOPS per core. And I bet if we do our work together and keep tuning, that can be 10 million. There's no reason not to. If you look at Ceph, we've done with CAS, I mentioned this earlier, CAS framework tuned for Ceph. We gave about 5x improvement using Optane DC SSDs. On Cassandra with a key customer, we actually were able to drive an 8x database performance increase using persistent memory. Now, persistent storage we can talk about, but persistent memory solutions. We actually gave them also a 3x TCO advantage by reducing the number of servers they needed to have for that encapsulated storage content. And the last one, which isn't as big a number, but I think it really is when you think about the world, we were able to achieve with vTune amplifier on Netflix a huge improvement of about 2.2x on their streaming workloads. And that matters, I think, in the world of compute when you realize that 30% of all internet traffic every evening is Netflix. So if we get them 2.2x more efficient, that helps, I think, the world, right? Fewer data centers, a little less power used. If you aren't familiar with vTune, we actually have done a huge amount with vTune Amplifier. We released this, I want to say, in February of this year. Keep me honest, Dan. I believe it is February of this year. The latest version of vTune. vTune Amplifier now supports DC persistent memory, so you can use it to understand hardware configurations out through the memory bus and help optimize software. So that is how we were able to do this work with Netflix. And that actually was so important to Netflix as a user of Amazon that we ended up partnering with Amazon to expose exactly these same features in their public cloud. So it is really, we have these pretty graphics that talk about core to edge and these different use cases, but that's an exact example of Netflix own CDN servers, how we were able to deliver more performance, and then how we were able to move that into a public cloud flexible model that actually supported our users better. So in this storage conversation, no storage conversation is ever complete without talking about the criticality of the network and the level of innovation that is required to actually be effective doing storage at scale across core to edge. You may be aware that in July of this year, we closed an acquisition of Barefoot Networks. Currently still a separate business unit, but absolutely complementary to our overall network portfolio. And what I'm showing here is really just a typical hyperscaler connectivity point, right? So we've got our different top-of-rack switches over various servers, and those servers are usually optimized for different use cases, right? We have a standard compute storage server. We have, accelerator pools available to us, usually with different connectivity between the storage and the accelerator pools as we would for a standard sort of server. This is why innovation is so important across this portfolio and together. Depending on that network connectivity, whether it's a fully routed CLOS or a folded CLOS network, you may have significantly more bandwidth in your rack than you do across your spine. And so workload placement really matters. And our customers are optimizing at that node level to make sure they're doing the right things to get to their storage tier for their specific applications. You may know that we introduced, I believe in March of this year, our Columbiaville Ethernet 800 series. And this is where we actually have brought to market a 3-in-1, right? The ability to do iWarp or Rocky V2 on top of our standard Ethernet adapter and support various fabrics on the back end. So really excited about how this actually simplifies hardware choice and selection in the network adapter card to support storage. But what are we doing specifically with the 800 series for storage? The one I'm most excited about is application device queues. So to use a simple analogy, right? Typical TCP, everything's all on the same bus all the time. It's just a big old mess, right? And one of the reasons why RDMA is so exciting is that folks can be a little more specific about congestion control and management. What you can do with ADQ on top of just standard TCP, NVMe TCP, is you can actually direct, so lower is better, not typical here, but lower is better. With TCP ADQ, you're seeing about the same performance characteristics on the bus as an iWarp or a Rocky V2 implementation. And this is just standard ADQ application, really exciting for us. So in case you are interested in learning more, it actually has been released for comments this week. So we're working actively to upstream ADQ into the Linux distro. I hope that you'll be part of the community participating in driving comments and getting this to closure, because it absolutely will allow the entire community to get better performance on standard networking appliances. which is hopefully our goal. So I won't spend too much time because I know I'm getting the hook very soon. But to go back to that network topology conversation, when we really see these different customers with folded or fully routed cloths networks, you see a very different storage design. You see a very different orchestration and workload placement paradigm, and a very different desire for offload and acceleration on the infrastructure side. So Facebook did a great conversation or a great post around their fabric networking solution, and what it really showed was the east-west bandwidth congestion. And most of that is actually internal logging, data structures, storage. It's the stuff that gets generated. They said 92% of the traffic was the intra-traffic, not the inter-traffic out to users, right? It's all of the stuff that we are trying to store and collect and manage that needs to actually be processed. And similarly, we're seeing with other customers going to, instead of that tiered structure, where they're controlling network cost and caching more locally to help ensure they have the highest sort of performance for their end solutions, the fully routed cloths, right? And these are where they're trading off and they're saying, we'll spend more money on networking and we will have storage pools and we'll get less stranded capacity, but you have to have a very, very fat pipe to feed that, and a really good methodology for orchestration and management. So we're seeing both extremes in hyperscalers, all kinds of hyperscalers. And each one requires a different storage topology, methodology, and management. And that's why it's so important to have very fast local store, whether it's persistent memory or Optane DC SSDs, or standard SSDs, hard drives, et cetera, right? There's a whole spectrum here. It exists for a reason. There's a totally different network topology. Out of all of this, my true call to arms are standards. Standards really do help us, and I'm so glad to see this community here together. Standards bring calm to the chaos. I said it before. Intel's incredibly committed to this community. We have so many folks sitting in this room, whether it's Jim or Alan, Jenny, all helping to drive these standards together and to help us make better products to solve the complexity of this ecosystem. So I know I got my 1 minute. It's time. So thank you so much for your time. We talked across kind of the nature of compute, network, and storage, from the edge to the core, how those are interrelated, how we can use standards to help, what the different software solutions and technologies are that Intel is bringing to market, including tools like vTune to help our customers get best experience across that ecosystem. And I hope that we can work together to do even more in the next year. Thank you so much. And who's up next? I'm going to take... I won't try and touch it. Are you doing your laptop too?
I don't need that thing.
We're going to close out our morning main stage for today with our speaker, Brad Settlemeyer of Los Alamos National Labs. I had the opportunity to hear Brad speak at Flash Memory Summit a few weeks ago in the persistent memory track. He's a senior scientist at Los Alamos National Labs HPC Design Group, where he leads the storage system research efforts within Los Alamos' Ultra-Scale Research Center. Today he's going to speak on a very important topic to all of us, high-performance computing and artificial intelligence and designing storage systems with them. Welcome, Brad.
Thank you. So I am Brad Settlemeyer, and this work couldn't have been done just by me. There's obviously a lot of people that were involved, and I real quickly just want to make sure I at least put their names on the screen and you can call all of them and ask them about all the great work they did here. I want to try and cover 3 things in this talk. A real quick, like 6-minute maybe, discussion of what simulation science is, HPC storage systems, how we construct them. Then I want to real quickly introduce DeltaFS, talk about designing a data plane for a metadata monster, how we got from millions of file creations per second to billions of file creations per second. And then finally, I want to move beyond DeltaFS and talk about converging storage for HPC and AI. So I always like to draw a picture of an example of an HPC platform. So what you can see on the left-hand side is the gray compute nodes that's connected by some kind of network. Here I've just drawn it with a very simple little 2D torus. But that's where the compute jobs run. And so the compute jobs run in such a way that you're running across, say, 1, 2, 3,000 nodes, 128,000, 256,000 cores. And you're going to run for some amount of time, and you're sending messages all the time to try and collaborate on this calculation. You're doing some big distributed DGEM, some big distributed sparse array. And then you got to pause the simulation. And you're going to pause it, and you're going to take all the memory state, not all, but 25 to 75%, and you're going to jam it down into the storage system. And you do this for reliability, but you're also going to do this for later analysis. And so this is kind of the critical thing to understand about the HPC workflows, that we're going to compute for some amount of time, but when we're running across thousands of processor or thousands of nodes, hundreds of thousands of cores, we're going to take errors. We expect about once every 24 hours on a system like Trinity, we're going to take an error. And so you can see that we've got to get that data either to the edge, where we have some storage on the edge of the platform, what we call burst buffer nodes, or through a set of routers that are going to take us out to a parallel file system. So this is effectively what you get on something like Trinity. You're going to have a tightly coupled parallel application, and then suddenly you're going to stop, you're going to quiesce the network, and you're going to have to dump all of memory as quickly as possible into some kind of fast storage tier. And so within the Trinity system, we have 19,000 nodes. We have 2 different types of processors. We have Haswells and we have KNLs, so on the order of 1 million cores. And you have a burst buffer that's about 3.7 petabytes, 3.3 terabytes per second. The file system we run on the burst buffer is the Cray Data Warp file system. I'll talk very briefly about that. It's a slightly relaxed POSIX consistency file system. Below that, we also have a Lustre parallel file system. It's actually split into 2 file systems so that we can service it correctly. So it's 2 596 gigabyte per second file systems. Each one's about 35 petabytes approximately. And then below that, we have a longer-term storage tier. And so one way to think about this is the burst buffer, you've got 4, 6, 8, maybe 24 hours of storage. Within the Lustre file system, maybe you're talking about 12 weeks, 16 weeks of storage that you can leave your data there and not feel like you're eventually going to be under pressure or some admin's going to tell you to get your data off the file system. And then down in the campaign tier, which is much slower, it's a mix of shingled disks or it's tapes. You're going to see that you can leave data for months as you need. And that's important because our jobs may run, I think the largest simulation that I'm aware of that we've done was across approximately 4,000 nodes for about 7 months. And so there was a lot of faults, there was a lot of state, dumped a whole lot of 35 terabyte state files, created hundreds of terabytes of analysis data. And that's kind of the basic workflow. So I just wanted to make sure we all had that background. So what is the problem with our current file system structure? So we use parallel file systems. This is kind of they aren't a descendant of distributed file systems. Instead, they're kind of like a sibling. They both started in about the same time, I guess. Our current parallel file systems were kind of started from an effort in about 1999. We run a lot of Lustre, but GPFS has a similar type of file system and has a similar history. PFSs are great whenever it comes to assembling a whole ton of peak storage performance. If you want to get a bunch of petabytes together and several terabytes per second of capacity, or terabytes per second of bandwidth, PFS are great. They have fixed layouts, so you can get all your spindles active, you can get all your SSDs active, you can get a really wide stripe, and you can get a whole lot of material pushing bytes at the exact same time. Really prefer very large requests. We're tuned up for large requests. We're trying to do this bulk synchronous. Our applications are not as great at it as we would like. We're under intense memory pressure on the applications. They're using 70, 80, 90% of memory. So we don't have that ability necessarily to build big buffering layers, but we do try to do some shaping on the I/O. So we will have something. But for our big application, we get a mix of like 12 megabyte requests whenever the buffering is going well, but 32K requests whenever things are going poorly. And again, you're dumping it out as quickly as possible. So you don't necessarily get as much time to shape the I/O. You want to have that storage active at all times. these file systems tend to relax consistency slightly, and this turns out to be perfectly fine. Data warp is what you would actually call like a byte level coherence is the consistency scheme. It's not quite as bad as like closed to open, but as long as you don't write in overlapping regions, you get a pretty manageable consistency semantic. And we always prioritize write performance over read performance. We are the kings of write once, read never. The goal is to not have a failure and never need that checkpoint. And then you can shrink your analysis data, and maybe you can only look at the last one of those if that's all you care about is get one number at the end. Our problems are, what about other I/O types? So namespace mutations and accesses generally don't scale well with hardware. Whenever you look at our metadata servers, we're not bound by the devices that are on it. It doesn't matter what device you put on. A lot of what we're bound on is how fast we can spin inside of locks, how fast we can get access through some directory where we've got to spin through some kernel infrastructure. File create performance within a single directory is particularly bad. And poor support for these small requests, anything less than a few K. What we're going to talk about today is 48-byte requests for DeltaFS. Those are particularly challenging. We're not a great IOPS workshop. And then just real quickly talk about them. Compared to the modern DFS, we're not anywhere near as good at like adding storage. These are not scale out. These are forklift upgrades. You drop it on the floor, you put all your storage on it on day one, and that's pretty much all you can do. Took 7 minutes. Okay, so quickly moving on to DeltaFS. I want to give a quick review of DeltaFS, or maybe a little bit longer review of DeltaFS. So DeltaFS is a project we did with Carnegie Mellon, Lionel and Carnegie Mellon. And the lead grad student is here, and I'll talk a little bit about what he's going to talk about a little bit later. But DeltaFS was designed to be a scalable metadata plane for HPC clusters. And so it's built on a few tenets. It's got scalable metadata performance. It actually didn't even have a plan to have a data plane. The whole idea was maybe you'd run it on top of something like Rados or some object storage system. But then as we tried to push into these absurd numbers like 1 trillion files, it became necessary to put a type of data plane on it. You're not going to write terabyte-sized trillion files, or at least we're not. And so it's got log-structured metadata. It's a no ground truth namespace. I'm not going to describe much about that today, although Ching will later. It accelerates file creation in a single directory. I'm going to talk a lot about that. In particular, the technique called an indexed massive directory, and that's how we can get this massive create rates. But we're also going to talk about how we're going to accelerate small writes. I've heard it called the dribble write problem. We're going to be writing out data 48 bytes at a time. And then I want to show an example of how we accelerated a science workflow. Okay, so we're going to go back to our picture of a platform. And this is kind of giving you a little bit better idea. So you can see that we have a lake of compute nodes out to the left. And then we have a storage system far out on the right. And then we have like a burst buffer maybe on top with the dark blue. And we have the gateway nodes that can bridge the networks, bridge between the two network types, some kind of high performance interconnect on the left, and some kind of high bandwidth InfiniBand connection on the right. And what you can see is that we have dedicated file system servers in this case. And I drew 3 purple boxes, dark purple boxes at the top to kind of show the metadata service. And this is one of the problems we have. So we can create a metadata service. Maybe we can do a little bit of DNE2 or DNE1, and we can get a few metadata servers. Maybe we can get 6 or 10 metadata servers, and it'll scale kind of somewhat okay. But it really constrains how we're going to design that platform on the left. If the deal is I want every single core, and I've got, say, 10 million cores to create a file in 10 seconds, well, I have to provision that metadata service for that system design. And so it really constrains what I can do in system design. I can't have 50,000 nodes, which is what Aurora was talking about and why they're looking at systems like Deos. I just can't get a create rate, a metadata rate that can actually do that. So the file system is unfortunately going to constrain our ability to design a system within some degree. We can't get the kind of create rates. And I can buy $75,000, $100,000 metadata servers, but I still can't really get them to perform at those rates. I mean, what I'm really buying is platinum processors that are quite expensive, just trying to get a little bit more churn. What I'd really need is a 10 gigahertz processor to get more performance out of my metadata service. And so the key idea with DeltaFS is client-funded metadata. So how do we push the metadata work? We've got all these great servers out here in this lake of compute. They're perfectly good servers. They've got perfectly good processors. Why can't we do the metadata out there? And so this is the first key idea of Delta FS. Transient Delta FS servers that you can stand up on demand and establish a namespace, scalable namespace as you need. Here I'm showing that there's actually, you don't just have to do 12 or 15. In our case, we're actually going to do 4,000 metadata servers whenever I show you the trillion creates, 128,000 total servers. So well, even 256,000 servers, I guess, in the very biggest examples we did. And so you have to change a lot of things to do this. You're going to change the namespace semantics. You heard the talk earlier about relaxing the data semantic. And the way you accomplish this is you relax the namespace semantic quite a bit. So we're going to eliminate provisioning dedicated metadata services for peak bursty. We're instead just going to have a metadata service that's dedicated to address all the objects in our file system. We're not going to worry about its performance. And we're going to stand up Delta FS servers to meet our performance demands. So we're going to need some way of doing some kind of bulk metadata operation. We do this by using an LSM tree organization for metadata inside the transient server, so it all get logged. This builds upon the lessons learned in TableFS and IndexFS. And this really suits HPC workflows where we can actually co-locate metadata with the application pretty easily. Again, we're going to quiesce the network. We get to reuse all of those resources while the application's sitting there doing idle. As long as we don't use any RAM, we're okay. We can borrow the cycles. So we've got to keep the memory image quite small. And the easiest analog to think of it is it's kind of a Git model for file system namespaces. You're going to check out a version of the namespace, modify the namespace locally, then do some big bulk insert back into some notion of a global namespace. And of course, the problem is you have to handle conflicts. And not to steal what Qing's going to describe earlier, he's going to describe all the caveats that come with this in a talk at 1 p.m. But the answer is we don't handle conflicts. We only resolve them whenever we have to. We want to be real lazy in how we do that, because having a strongly consistent namespace is going to go much slower. And so this will get you some really great performance. I mean, Delta FS can absolutely rock and roll for creating files. So if we look at what Lustre can do, maybe you can get 100,000 creates. Maybe that can be pushed up to creates per second. Maybe that can be pushed up a little bit higher if you work hard at it. Delta FS is going to drive you right into the millions pretty easily. You stand up a bunch of servers. But what if we want to do billions of files per second? How are we going to do that? And so that's what the remainder of, or that's what the second part of this talk is now. And so we're going to use something called an indexed massive directory. And this is Delta FS key idea number 2. But in order to start talking about this, I want to real quickly talk about the application that motivated it. I mean, why would anybody really need 1 trillion files? It's kind of an absurd thing to talk about. So this in the background is a VPIC simulation. What's happening is a charge-neutral plasma is being formed. So we have a bunch of electrons and a bunch of positively charged ions, effectively positrons, and they are sliding across each other to create a plasma in space. This is the kind of thing that we simulate at Los Alamos. We're interested in plasmas. This is an astrophysics thing that can happen out in space when you're creating a sun, I guess, or something. So what you'll see is you'll have these magnetic reconnections, and we have these things called magnetic islands. And each one of these colors here is actually a particle. These are massless particles that we're showing, and this is on the order of trillions of particles that you can see because you've got quite high resolution in this picture. And so VPIC is the vector particle and cell code that we use at Los Alamos. Super efficient, runs across thousands of processes easily, hundreds of thousands of processes easily, scales like mad. Very efficient computation infrastructure. And so effectively what you do is you take space and you subdivide it into a mesh, exactly like you would think. In this case, it's a fixed grid, super easy. The particles are 48 bytes. They have a momentum and a position, and that's really about it. And on each process, we're going to have about 2 million particles. We've also got a set of fields that are associated with the grids. The end result is we've got about 10% of the memory left. VPIC and the OS require about 90% of the memory on the nodes. And the scientist wanted to do 1 trillion particles. And in particular, what he wanted to see was which of the particles would take a high-energy excursion a high-energy excursion. And what they do is they'll vibrate between 2 magnetic islands. At least this was his hypothesis. It's been known for a long time they'll vibrate due to collisionless shocks. But he had this theory that they would vibrate due to connections between magnetic islands and take off into this high-energy regime. And so the problem is you're under intense memory pressure to store the current state of the particles. You have no hope of storing the history of the particles. And you don't know which particles are going to vibrate and enter a high energy regime. In fact, you don't even know that this really happens yet. So he wants to look at this and determine this. And so the way you would do this in a traditional system, so if you took delta FS and you combined it with just some kind of regular backing store, is you're going to create a file at every process. You're going to create a log, and then basically you're going to take a 4 megabyte buffer, accumulate 48 byte particles, and then fill the log. Just do appends into the log 4 megs at a time, get fantastic rates. So it's a really great I/O pattern for shoving the data out the pipe as fast as possible. And there's about 40,000 time steps, and about every 500 time steps is enough resolution to catch the vibration. So you can, I mean, the time step here is on the order of a nanosecond or something. And you're discretized in time, capturing the position of all the particles. So this is a great figure. So if you look at particle A, which is in the first time step, it's in the left-hand process, and then later, particle A with the little red line behind it is in the second process. This is because the processes are, of course, moving at relativistic speeds. They're moving all through the mesh. They're reformatting. They're vibrating at best between these magnetic islands, if our scientist is correct. Then the only way to actually access this data is to either, once I've written out all these terabytes of particles, is at the end of the simulation either do an exhaustive search or sort all the particle logs, depending on how many particles you actually want to retrieve. Those are basically the two ways of doing it. Either way, you're going to take Trinity, and you're going to reuse all the memory to do some big tera sort or some big tera search. Those are kind of the two ways to do it. And the key idea is that we can't figure out what the interesting particles are at the beginning. We want to just go find the ones that had high energy and then look back in time and see if they actually vibrated back and forth. So our great idea was, well, wouldn't it be a whole lot better if we could actually just do a particle per file, and at the end of the simulation, you say, well, I care about these 10,000 particles. They have high energy. And rather than sorting some big log, can I not just go, OK, I'm going to open file A and read its history, then I'll open file Y and read its history, and I'll just read back through the history of the particles. I'll effectively use the file system to index all the data. So suddenly we've gone from creating hundreds of thousands, possibly millions of files, to now we want to create 1 trillion files all in one directory. We want every particle in a file. So how are we going to do this? So here are kind of the 3 candidate approaches. So the first approach is the traditional approach we talked about, where we're actually going to do a big post-processing step. We're going to need about 1 terabyte of RAM at the end to search through all of those particle logs. The second one is we could kind of do the same thing. We could create a file system that could create 1 trillion particles, but we still have to solve that problem for writing out 48 byte writes. So every time I do an F write on 48 bytes, I've got to figure out how I'm going to get that data buffered up. We're not going to do 1 trillion 48 byte transactions and it finish in our lifetime. It's just going to be too much. Even if it's SSD, it's just too small. Network costs, you get crushed. And so we could have this notion of somehow we took dedicated servers and set them up as an indexing pipeline so that we could fill this data into a big container that's indexed correctly. And we could have these dedicated servers that would buffer up each of these files. We could do a technique like partition file domains, have nice big 4 megabyte buffers for something on the order of 1 trillion particles. Well, we're starting to talk about a lot of RAM here, just as much RAM as the simulation has. Maybe not quite that bad. But we're going to have dedicated servers, and that's just antithetical to the idea of delta FS. We don't like dedicated servers. We want to do everything as this transient service that you can stand up and tear down on demand. So that's the last approach on the right. So how are we going to take delta FS? We're going to tag all this data as it goes into the index massive directory so that we can pull it out a file at a time. And so somehow we're going to do this, and we're going to do it just using 3% of RAM, because we don't have enough RAM inside to do a whole lot of buffering. So somehow we're going to get all this performance out of this system by only using 3% of RAM to shove 48 byte particles into much bigger logs. Obviously, we can't write out 48 byte particles. So this is a delta FS index massive directory. So on the right-hand side, you can see kind of the logical idea of the concept. So again, we have all these processes. They've all got just a random collection of particles on them. And the very first step we're going to do is we're going to shuffle all the particles to a home location. So every particle has a home. We're going to use a hash function. A partitioning function is the way to think about it. So now we're going to have, again, in the largest case, we've got 256,000 processes, so 256,000 partitions. We're going to run with 200, directory is going to be composed of this 256,000 partition deep, where we can actually just immediately hash to figure out where this file is, and we can immediately cut the space down by at least 256,000 times. Then inside of there, we're now going to figure out how we're going to accumulate the particles into some kind of buffer so that we can write those in. We're again going to take the same idea that we used for metadata. Metadata is a very similar problem. It's small updates. So now we're going to actually log the data with the actual file name. So we're going to actually expose kind of a log structured merge tree. Except we're not going to do compaction, because compaction would again crush us. So in this case, we're just going to write the data out into hash tables. And so what you can see at the bottom is that if this all works correctly, what we're going to have is we're going to have an index for each of these partitions so that we can rapidly go search files out of it. And rather than searching terabytes of data, we should just be able to go pull back a megabyte of data to read the index and then immediately go dead reckon for our particle trajectory. So the implementation is shown kind of up here in the upper right. And so what you can see is that there's a big shuffle pipeline, and this is based on the Mercury RPC package. It's actually one of the technologies that underlies Deos that she was describing in the last talk. They use Mercury RPC as well. It's a highly efficient RPC package. It takes advantage of our low latency networks. Even so, we're still going to have to package things up into 64K buffers in order to drive the network in the bandwidth regime rather than in the latency regime. I'm not going to have time to talk about how we did all that, unfortunately, but we effectively implemented a software dragonfly routing scheme inside of this shuffle layer. Then once you enter the delivery queue, now you're going to get the buffering so that you can actually buffer this up. You're going to buffer up particles randomly, and we're just going to use an LSM tree. So we're going to fill a mem table with key value pairs of particle ID and trajectory, and then we're going to spill those to disk. But rather than spilling them to disk as SS tables, we're going to spill them as hash tables, but they're really kind of approximate hash tables. There's no point to do a full compaction or even a full sort here. Instead, what we're going to do is we're going to create a filter block for a mem table, a index block which describes where within the data block, because again, lots of 48-byte particles, where within the data block to look, and then we're going to be able to cluster that entire index, as you can see down at the bottom, so all the filter blocks and index blocks, we can retrieve those for a single partition. Now, one of the things I talked about a little bit earlier is maybe there's more than one partition per server. And this is because we can't actually calculate the filter blocks, the index blocks, and spill to disk and keep the disk busy all the time. This is one of the key ideas within DeltaFS, is you've got to be bound on the disk. That's the slowest piece. You have to be pushing to the disk at all times. And so, in fact, we have to have 4 mem tables active at any particular time so that we can make sure we've always got something that's spilling to disk. The calculations aren't intensive to calculate a filter and index block, but even so, we really need no pipeline, no pipeline gaps to be able to get the maximum performance. And so this is how it worked. So on the left-hand side, you can see the overhead. We're writing out more data. It's about 3 to 5% more data for those index blocks. So effectively, we've turned a directory into a set of silos of partitions, quite a few partitions, 4 times however many servers we have. Number of processes, which is also the number of clients, and the number of servers is along the bottom. So you can see once we get out of the regime where we've got the startup, the light blue line is showing that the performance is fixed for the baseline case. And this is because we're holding the number of burst buffer nodes fixed to make this much simpler to think about. We're going to maintain a 32-to-1 compute node to storage node ratio. So we're going to write into that file system at 32-to-1. So you can see that, in fact, the baseline performance is fantastic. It really can shove a file system full. And DeltaFS is a little bit worse. We're about 8% slower, which we're only about the data is only about 3% larger. So you can tell that the shuffle comes with some cost. The shuffle isn't free. There's a lot of work. And then as we get out, you can see that the shuffle algorithm starts to really run out of steam at really large scales at 128,000 cores. We're up at 35% slowdown. It's not too bad whenever you look at what comes next, but it does cost a little something to shuffle the data, in particular as you get as the ratio of bisection bandwidth increases. We're using a lot of the network at this point at 128,000 cores. That's 4,000 nodes at that point. So the right-hand side shows how long a query takes. And I can't really scale the queries all the way out because it would be irresponsible to run the baseline at much larger than this on a government resource. So it's about 10 minutes in the largest case to do the query in the baseline case. It's about 543 seconds, whereas you can see that the delta FS, where you read in the clustered block, is always less than a second. And in fact, if we took it out to 128,000, you would see that delta FS would be about a half a second to actually retrieve a trajectory. So you can retrieve, I don't know, 10,000 trajectories in about an hour here, whereas it would take on the order of 6 months to retrieve 10,000 trajectories. And as part of this, we created 1 trillion files. And I don't know that there's a world record for this, so I didn't write the headline on the world record part. But I don't think many people have created 1 trillion files in about 2 minutes. So it was a pretty stunning create rate. And the key takeaway that I want to talk about here is it's really only possible because of the techniques from key value storage. By blending those with the file system and creating a directory container that is effectively a key value store, where we're logging all the metadata and logging all the data, we're able to get these incredible rates. And so now this leads to the final part of the talk that I wanted to get to. And we're actually here with enough time that I can talk about it. And so beyond delta FS, trying to look for converged data models for AI and science. And so this is one of the things that we're really interested in, and the kind of the lessons from the indexed massive directory really drive this analysis that I'm getting ready to talk about. So this is an example of a different kind of simulation. This is called an adaptive mesh refinement technique. This is an AMR mesh. Having mesh in there twice is a little weird. And what you can see is it looks like there's like these little pillars kind of in a fluid, like it's in an aquarium, and the water is kind of moving and it's swirling around. And what you can see, if you look at the refined area, is that as there's more turbulence, the mesh cells are going to be smaller. And we do this for memory saving, right? If there's no energy or there's nothing happening in a cell, we want to take up as much space as possible and not have to waste any memory storing the state of that cell. And so if I were to run this simulation as a movie, which after watching the awesome talk earlier, I should put movies in. But you would see it refining and de-refining as those turbulence twists around those pylons in a liquid. And so the question I always ask whenever I look at this mesh is, well, how many rows are in each of these columns? And it's, of course, a trick question. It's different, right? And you can even ask it in the more funny, which is how many of these columns are in each of these columns. And what you can see is that it's an unstructured mesh. There's no way to make sense out of this. And so whenever I try and map this to a one-dimensional array of bytes, or a file, as we know it, there's really no reasonable way to do it. I mean, you can do something silly where you try and space out and have big sparse files, and you do some mapping, but depending on the levels of refinement, it gets crazy on you. And the answer is what people do is they actually store it in a bunch of files. So what they do is they take each of these levels, and they store the largest level in a file, and they call that the level 0 file, no relation to LSM trees. And then there'll be level 1 for each of the refinement levels. And usually there's a limit on how much the simulation package will allow you to refine space. So maybe you can go up to 16 levels or something like that. And there's a bunch of constraints about how much you're allowed to refine around some area that the simulation will be enforcing. And so what you'll find is that the first file you can store in some order. You can do it in maybe row major or column major order or a Z order, which is a space filling curve. And I'll show an example of that a little bit later. But when you start talking about the other layers, or the other levels, effectively the data is randomly refined. I mean, you're simulating it because you don't know what's going to happen. You're under memory pressure. You can't sort all the cells. And so effectively what you have to do is you have to shove each of the levels down with their metadata describing their exact location. So you end up just having to write the data out in random order after the first level. And this is a problem with mapping down to a one-dimensional array of bytes. And so you remember me talking about the key value. So one of the things that we always try and look at is, well, what are other people doing? So we went through and we did a quick analysis of, I'm in the furthest left-hand corner. I'm simulation science. So we looked at other sciences, and we just look at the number of keys. We've got 1 trillion keys for 1 trillion mesh cells. The molecular dynamics and the bio guys, maybe they've got 1 billion base pairs, maybe 1 billion atoms at the absolute outside. The AI people have maybe 1 million parameters in their parameter space. They do have trillions of training files, but that's big bulk data. It's not exactly representative of what you'd see in a mesh. And the graph analytics guys are kind of similar. They had 100 billion nodes or edges in their graphs, and so maybe there was some issues that we could borrow. But then you look at what they do, and it's a read-intensive workload. But then recently, a great thing happened. The AI folks started doing outrageously large neural networks, these ensemble mixture of experts methods. And I am by no means an expert in AI, but I am super excited by this idea, because finally we're lined up. Simulation science with our trillions of keys, AI with their trillions of parameters. Our values are maybe a little bit larger, but it's very, very similar, and it seems like we finally got a chance to converge with those guys. So if you look at the different operations that we have here, so as we're a throughput write shop, so we're going to take all our keys and we're going to use techniques like index massive directories to bundle those up. We won't always be as bad as 48 bytes. In general, we'll have maybe 10, 12, 14 doubles. That'll be our kind of what's in a cell, maybe 50 doubles at the outside. So we're gonna need that ability to do bulk inserts. We love range queries. We want to be able to track where those phenomenons, where that wave is moving through space or through the aquarium. Also interested in point queries if we want to do particle analysis. Other sciences are kind of similar. They're going to do maybe more point updates, maybe more point queries. And in the case of bio, maybe a lot of mmap, which is a little bit hard to figure out exactly how to map that in as a key value work. Might be possible. The mmap semantic is so strange. But you look at the AI people again, and here we are. So now, it used to be the case you'd say, well, all they're going to do is they're going to read a parameter, recalculate a new weight, and dump it back on. But then you look at projects like PipeDream and Boson, and they're all going into this model where they try and relax the stochastic descent as much as possible, and they want to batch up these updates. This looks exactly like HPC again. So here we are where we can see a chance to converge in how they're doing their updates. They're looking at how to do a more efficient update on these massive models. The training data is, again, bulk retrieval. I don't know exactly what to do about that yet. And then, again, we have these point updates, or these point reads at least, with the graph analytics workload, where they're trying to maybe they're calculating new weights for the edges, or maybe they're doing pointer chasing through some massive graph to find relationships, and you bought this, you would like to buy this instead. And so we can see that there's a lot of similarity in the workload. And what we can also see is that while HPC is currently a decent amount larger in how large we run our jobs, it's certainly true that the analytics that you see from something like Microsoft Cosmos, where they have these massive 50,000 node clusters, far, far larger than Trinity, our biggest system, that they've got this capability to run massive graph analytics. They just maybe haven't told me about it, which is fine. They don't have to tell me anything. And we're starting to see, I think, with these outrageously large neural networks, maybe that we don't know exactly what the largest training processes are, but I suspect there's been trainings that are on the order of 10,000 nodes. But for sure, they've done trainings at 1,000 nodes. And so the only real problem we have is maybe there's a little bit of difference in what the values are in a key value store. That we're 10, 12 doubles maybe, whereas when you look at what the AI workload is, they're trying to shrink the precision down. They're down to 8, 6-bit weights or something like that. That's a little bit of a difference, but we're still very, very small. We're still way under a block in both cases, so way less than 4K. And if you look at graph analytics, those guys have the worst of it all. They're always a pointer. They're always chasing a pointer, updating a weight. And so what I think we want to look at is prying open the index massive directory, not even putting the fwrite shim over top of it, and instead just exposing the key value to the application and very easily building very thin shims that can turn a parameter server for an AI workload into a mesh server for an HPC workload. These are the same data structures that we've always been using in file systems. It's B trees, log structured merge trees. These are all key value stores effectively. It's just different ways of iterating along the bottom of the B tree, the nodes at the bottom. But rather than hiding it under a file system interface, we need to actually bring this interface directly into the application. I think that ROX and LevelDB have all demonstrated that this is an application interface that's useful for applications, and it's a chance for us to build a big distributed key value store that really suits all of us. So for HPC, we're going to need a little bit of HPC research. We need to use our low latency networks. We're pretty tied to that. It's important that we're able to leverage those. But we also have these indexed massive directories. But we also get this one huge gain. So I talked about how it's difficult to map a mesh space onto a closed one-dimensional byte. But a key space isn't one-dimensional. A key space is an open range. So you can actually keep refining the key. And so we just borrowed the technique from the Farsight file system that Microsoft prototyped a few years ago. And we just used dots to separate the levels of refinement. And we can just tack it all in there and iterate over it in order. It's super easy. And so this is already a huge gain in simplicity for how we can begin to look at our meshes. And so this is an appeal to do a converged system software for AI, HPC, and analytics. Let's get some of the building blocks together. I don't know whether it's indexed massive directories to act as containers, a hierarchical way of accessing key value stores, relaxing the namespace consistency is something that DeltaFS has pushed a great deal. There's non-POSIX consistency models. Those are already pretty common. So it seems like we have the chance to do this and build storage systems that can converge all of these different workloads and maybe allow you to tune the trade-offs that you make all through the same key value interface. So to summarize everything that I talked about, brief overview of HPC platforms and simulation science. You can read a whole lot more about that in an article we had in Login magazine. A brief overview of DeltaFS. This is the paper that introduced DeltaFS and its scalable namespace. And Ching will talk a lot more about that at 1 if you want to hear a whole lot of gory details about how to relax namespace consistency. Indexed massive directory overview a couple years later, and how we scaled it up to 1 trillion files last year at SC. And then finally, the kind of stuff that I'm reading, trying to learn about ensemble learning models, outrageously large neural networks. Thank you.
Are there any questions?
Everybody's hungry.
Okay. We'll see you after lunch.
Thanks, Esther.
Sorry I had to sprint out of here.
Oh, that's fine.